Welcome to part 5 of real-time systems development. Now let's have a review of where we've got to now. We're slowly building up our picture more and more. We have the world, that's us, that's what we're trying to control, and in the world there are these measurands. We have a whole host of equipment and techniques we've discussed to get these measurands into our computer. So we have transducers, transmitters, analog to digital converters, timer counters. Now these devices could be on a bus structure or they could be on a serial structure, I2C, SPI, touch memories, or we may get the data off of a network such as the CAN bus structure. Whatever it is, all these techniques are means to get numbers into our computer that are directly related to measurands. Then we decide what to do, and that's what we're going to deal with today. Once we've decided what we're going to do, we have these output devices we've referred to: relays, solenoids, optocouplers, digital to analog converters, triacs we've talked about. We've talked about the techniques of pulse width modulation and phase modulation. We've discussed two types of motor, stepper motor and DC motors. So here we have now all of the external hardware techniques. We've covered everything we need to know about how to get information out of the real world and how to act on the real world to drive it back to what we want it to do. Now we're going to consider what happens in the microcontroller. How does it decide what to do? So we're going to move on to a totally new subject, the subject of control theory. And I'm going to introduce to you some very simple control algorithms. Now, you can do a whole undergraduate course on control theory if you wish. It will take you 3 years. We haven't got 3 years, we've just got a few hours. So you're only going to touch a very small part of the subject. But a lot of it is just pure common sense. Let's consider the sort of diagrams we have to deal with. Now, typically, the way control structures are drawn is we have coming out of the system, the real world, is a variable that we will refer to as MV. MV is our measured variable. That's coming from our transducers, our ADCs, etc. The other input we will have is a variable known as SP. That's our set point. That's what we adjust. That's the control dial, or what we dial in the keyboard. So that's what we want. This is the reality. The output of that will be an error. What is the error? And the error is defined as the set point minus the measured variable. So if you're below the set point, that's always a positive number. That error signal goes into some function of time and displacement, whatever that is. This is what we're going to discuss. It will analyze that error, and then it will provide a control signal, CS, an output, that goes to whatever our actuators are, our real world system. We're not going to bother with that anymore. This is now a control signal that acts on the measured variable. So what we have here is what is known as a closed loop system. Why is it closed loop? Because we're continually monitoring the measured variable, comparing it to our set point, determining our divergence, our error. That's being fed into some form of algorithm that is then acting on the outside world and adjusting the measured variable. So there we have the overall structure, the way that we would normally draw a closed loop control system. What I want to start thinking about is what are these functions? What are these controller functions and algorithms? Because you're in KL, you can think about air conditioning. It's exactly the same thing. We are trying to maintain the temperature of a room at a particular stable temperature. The set point then is the temperature we want that room to be. The measured variable is the real temperature of the room. So what do we do? Well, let's take my heating problem, which is certainly our problem here at the moment, being the middle of winter. If the room is too cold, what should we do? Let's turn the heater on. Not a little bit, just turn it on. Get it blasting hot air into the room, warm us all up, that's it. In your case, you'll be blasting the air conditioning, cooling the room down, it's just on. So we have a very simple strategy. We either have our system on or we have it off. And there's nothing wrong with that. Don't look for complexity where there isn't. On-off control is very widely used, extremely simple, extremely effective, and it works. And if it works, why not use it? So let's look at the response characteristics of an on-off control system. Let's draw a graph. In time, we will have a fixed value. That is our set point. We want the room to be at that particular temperature. Initially, we'll be below it. So what do? We switch on our heater, we drive the temperature up. So for all of this period, we have the temperature on. So finally, we hit the set point. We'll probably go through it. And as soon as we hit it, we turn off. Now, what will inevitably happen is we start cooling, we start losing heat, and then immediately we turn back on again. So a typical characteristic will look like this. And that's true for any unidirectional system. A heater that is heating a room or air conditioning that's cooling it. You've either got it on or off. So what will happen is you'll rise to your set point and then you'll start switching between the two states, hopefully gliding along the set point. What you want is nice slow oscillations. This is a valid control technique. It is called on-off control. And the vast majority of controllers out there do no more than that. Either you're on or you're off. Nothing special about it. But it can go unstable. No matter what you do, as you rise up to your set point, you are eventually going to reach a point where you oscillate around it. As we saw on our graph, we're on, we go off, on, off, on, off, on, off. Why do we oscillate? We do that because nothing happens instantaneously. In the real world, by the time you've detected the crossing, that's been converted by the ADC, that's been transmitted over the bus, and it's reached the processor. There is always a finite period of time taken to gather that data. We always realise we've overshot sometime after the real event. So even though we have reached our set point there, our processor doesn't realise it till sometime later. So we will continue driving heat into our system until we realise we've done it. And we've switched the heating system off, and that command has gone to it, and the motor's turned off, and everything is turned off. Only then will we fall. Because these are real events in a real time. So there is always the processing time taken from the point where the real events occurred. We've crossed our set point. It's only some time later. It might only be milliseconds, but it can never be instantaneous. It always happens some other time. So you would tend to oscillate around the set point. Now that's okay if the frequency of oscillation is slow. Now with a room heating system or with an air conditioning, it probably will be. It will glide up, click on, click off, click on, click off, or in your case it's clicking on and clicking off as the temperature is rising and falling. Nice and slow. What happens though if you've got some very fast processors and some very fast actuators that can in fact respond really quickly, very, very quickly? What will tend to happen is that instead of a nice slow response, we will get a system with an extremely fast response instead. And if here's our set point, we'll rise up to it, we'll immediately realise what happened on, and we will get some very, very high frequency oscillations around the set point, extremely high speed. And that certainly will happen if you've got something that is very fast, very good. Actually, the better the processor, the more chance of this happening. And what will tend to happen is that you start exhibiting a phenomena that is known as hunting. What that means is that our measured variable is wobbling around the set point, always trying to find it, but missing it, but at very high speed, such high speed that the high frequency oscillation will actually cause physical damage to the actuators in your system. I mean, a computer can run at 20-30 megahertz, but a poor old solenoid or relay or opto switch, they can't run that fast. And what will happen is that you will burn out your control loop. So we've got to calm things down. We've got to slow things down and stop this happening. Now, in general, all on-off systems exhibit hunting. But what you want to happen is for the frequency of hunting to be nice and slow and smooth. What you don't want is the high frequency oscillation that will cause the system to destroy itself. So let's think of some techniques to control this process. The most widely used one, and the one that is most effective, is a process known as hysteresis. What we do, let's draw our graph again in time. There's our set point. Bear in mind, this is a unidirectional system. This is quite important. It's unidirectional. By that, I mean we can only drive it in one direction. So it's a single heater, or it's the air conditioning, or it's a motor that only moves one way. So you can only drive things in one direction. You have to rely on natural cooling or heating, slow processes to drive things back to rest. Now, if we were to try and control to this as it stands, we could end up hunting. So instead what we do is we broaden, we spread out the set point into what is known as a hysteresis band. We actually widen it. In fact, what we have is we have a plus and a minus hysteresis. And the way it works is that instead of stopping driving at the set point, we deliberately pull it through to the upper end of the hysteresis band. So if we're below, we stay on for all of this period through the set point till we hit the upper end of the band. So if we're rising, we deliberately pull the measured variable above the set point. Only once it's hit the top of the hysteresis band do we switch off and we start letting it fall. But again, we don't switch it on here. We wait till it's gone below, so it's off for all of this period, and only when it's below do we switch it back on. The result of that is that we slow down the frequency of hunting to something that is far more manageable. So while we're rising, we pull it through the set point to the top of the band. While it's falling, we leave it off until it's fallen well below the set point, and then we switch it on again. And what we tend to do is, you'll never get rid of hunting, but we've got it under control. And we actually now have the hunting process bouncing inside the hysteresis band at a much slower level. Now, if you want to go into the maths of this, which I am not, and you don't have to, there is a direct mathematical relationship between the width of the hysteresis band and the frequency of oscillation. That's common sense. I'm sure you'll see, if you go back to this picture, as you narrow this band, so this frequency of oscillation is much faster. Because the rate of rise and the rate of fall, these are constant. They're based upon the actual piece of equipment you've got. So if you narrow this band here, it will start oscillating at a higher frequency. So what you do, in order to get rid of the hunting, you widen the set point out and you trap the measured variable inside the hysteresis band, so it bounces up and down. So a hysteresis band is a way of stopping hunting in an on-off controller, and that is achieved by widening out the set point to be a band around the set point, positive hysteresis, negative hysteresis, and we keep on, while we're rising, we pull it through the set point and then we let it fall back down again. So hysteresis is a way of controlling hunting in an on-off controller with a unidirectional system. That is, you can only actively drive it one way. But what if you can drive it both ways? Here's an interesting thought. What would happen if you had a room with both a room heater and you had air conditioning? So you had a room heater trying to warm you up and air conditioning deliberately trying to cool you down. And let's assume we have on-off control. Let's have our set point again. Now clearly, if you're below the set point, you're too cold, the heater will come on until you reach the set point. And as soon as you go through the set point, you would hope the air conditioning comes on to cool you down. So what you can have happening is, again, the identical response characteristic. But think what happens at the singular point around the set point itself. And bear in mind, there's always a margin of error. It is actually possible to maintain the set point by having both the heater and the air conditioning. They could both be full on fighting each other to push you into the set point. Because if you have a finite processing time to process the data, by the time you've decided to turn one on, you could have moved into the other state. And it is possible, because it's a real system, not a simulated ideal thing. If it was an ideal world, this would never happen. But in the real world, it is possible, because of the time delays in realizing what's going on, you could actually end up with both units full on fighting each other, and you get perfect control. But what you're doing is you're burning out both units. So with a bidirectional system, you've got to do something different. I'll give you another example actually. An alternative example would be a machine tool. A motor, let's assume that's a drill, and we want to drill a hole. So we have to bring the drill to position and then drill the hole. Now that motor has to move both that way and that way to get the position correct. A very common phenomenon, especially if you're using on-off control with too high a gain, you may even have seen this happen with a machine tool. It overshoots the position, the controller brings it back, and it starts moving backwards and forwards rapidly, trying to get in position. But because you're always a little bit slow in finding out what's going on, you've overshot, you end up pushing back, and in fact that's where the word comes from. It comes from the machine control problem, where the drill on the machine tool, or whatever it is, could be a lathe, the cutting tool rapidly oscillates around the hole it's supposed to drill, and the whole factory stops because they're waiting for a hole to be drilled. How do we stop this? Well, again, you can use hysteresis, but to not confuse the matters, I hope, I'm going to give it a different name. When we're in a situation where we can drive in both directions, I want to instead implement a thing called a deadband. Now, in fact, a deadband is negative hysteresis. You can think of it as the same thing. The way a deadband works is that if you are capable of actively driving up and actively driving down, the hysteresis principle won't work. Because you could end up inside the hysteresis band with both of them on fighting each other. Instead, you still widen out the set point into a dead band, plus dead band and minus dead band. But what you have a rule that says if you're ever below the lower part, you're on for driving up. If ever you're above the upper part, you drive down. But if you're anywhere in the middle, both systems are off. Both of them are off. That's why it's called a dead band, because if you're inside the dead band, both the drive up and the drive down must both be disabled. And if you make that narrow enough, then what happens is you trap your measured variable inside this dead band. And if you go to the limit and you have the dead band as 0, then you will end up with both systems fighting each other to keep control. And that would not be a good situation. If they overlap each other, you've got into the hysteresis state, and then you really are in trouble. So, a dead band is used in a bidirectional system where you can drive the system both up and both down. So let's have a summary of on-off control. One of the simplest structures there is, and very widely used. And why not? If it works, let's use it. All we say is that if the measured variable is below the set point, we switch on. And if it's above, we switch off. And we get our characteristic response of rising up and then oscillating nice and gently around the set point. But the danger with that is that if your response is too quick, you can have very, very high speed oscillation. So to overcome that, we use hysteresis. And with hysteresis, as long as we're rising, we rise and pull it through the set point, and we only switch off when we're above it. Now we let it naturally decline by natural cooling or whatever the mechanism is, and we only switch our system on again once it falls below. So here we're on, and we're on through the whole of the band. Then we let it fall. So what's important is the direction of change. If we're falling, we let it fall below the set point, and only when we're below it again do we switch back on. Now the alternative structure is one where we have a bidirectional system. This is where we can have a motor driving both up and a motor driving in the opposite direction. In this case, we have to use instead a dead band. And what we do is we say if you're below it, you drive up actively. If you're above it, you drive down. But if you're in between the two, then you must have both motors, both systems, heaters and coolers, whatever they are, they must both be off. And the idea is that you will then trap the measured variable inside the dead band. Very simple. But there are, of course, more precise mechanisms. The on-off control structure, it was all or nothing. If we were well away from our set point, we've got no choice. We turn the whole thing on and we drive there as fast as we can. And when we hit it, we try and put the brakes on and stop. It's not going to work, is it? Well, it worked for a very slow system. For a fast system, it won't work. So why don't we, as we approach the set point, slow down? It would make far more sense to start pulling the power off as you get there and glide in very, very nicely. Why don't we instead go for what is known as a proportional control system? That is, the control signal equals some constant, the proportional control term, multiplied by the error. So the greater the error, the more we drive our system. The less the error, the less we drive it. And the idea is that we glide into our set point. let's look at what happens in real time. In the ideal structure, here again, that's time. This is measured variable. And if we draw in our set point, while we have a very large error, our control system will be fully on. It's virtually like an on-off controller at this point, and it's rising up very rapidly, trying to get us there. But as the error drops off, as that tends to 0, so the control signal tends to 0, and what we really want to happen, we are hoping, is that we would glide in nicely, and then we will hit the set point. Nice, smooth control. That's what we want. That is the ideal response. And of course, you never get the truth, do you? You never get the ideal response. Why is that? There's two reasons why you will never get the ideal response out of a real system. One is there's always energy loss somewhere in the system. No matter how much you try and heat a room up, some heat is disappearing because some idiot's left the window open. Or whatever the system is. The air conditioning is rapidly cooling everything down, but heat is still getting in to the room, warming it up. You always get perturbations. In a machine tool, whatever you can do, you can't do anything about it. You've positioned it beautifully, but there's always vibrations somewhere that move you off station. So you always have a whole load of extraneous effects outside of your system that are pushing you away from where you want to be. So even though in our ideal system we are hitting our set point, outside events keep on knocking us off of it. Now there's another characteristic that's very important. Time. You never respond to things instantly. You're always looking at history. It's taken time for the transducer to get the signal, to convert it, to transmit it, to get to you, for you to think about it, to run your program, to do something. There's always a time delay, by which time things have got worse. So you're correcting an error that you believe was there, but because you've taken so long to do anything, the error has deteriorated and got worse. You could never respond to the correct, true, instantaneous error. It's always delayed in time by a very small amount. And what happens is that if you integrate all of these phenomena together, you finally end up with a phenomena which is known as the steady state error. There's nothing you can do about it. All proportional controllers will exhibit steady state error, no matter how expensive, how fast it runs. You can't control the outside world. You cannot beat nature. Out there, something will knock you off station. And it's a random event. And it will always tend to drive you a little bit above the set point or a little bit below. So our actual response characteristic with a purely proportional controller, this is exaggerated, it always ends up looking like this. A little bit below, or it might be a little bit above, but it's never spot on. You never ever get the set point to equal the measured variable. That is if you use the proportional control structure. Control signal equals some constant multiplied by the error. Why? Because that error isn't the error now, it's the error from some time ago, and things have moved on and got worse. So you always have a steady state error in a truly proportional system. If it's only proportional, it will never get there, it will get nearly there, and that might be good enough. So again, you will find lots of control systems out there which are purely proportional only controllers. I mean, driving a car, in fact, is a proportional controller. Your eyes, they're the sensors, they're judging the velocity of the car, and you're adjusting the throttle of your car proportionally based upon your perception of velocity. That's proportional control. But there's always the processing time for your brain and for the engine to respond. So you're forever adjusting the throttle. If you have to go at a steady speed along, you're always adjusting all the time because you're correcting for the errors, the steady state errors in the proportional system. And human beings are quite slow in that respect. So proportional control is a substantial advantage on on-off control in that we close our control off as we approach the set point. Unfortunately, due to time delays, loss of energy, perturbation, noise, we always have a steady state error whereby our measured variable will always just end up at rest a bit below or a bit above the set point. So we need to have a mechanism to get rid of the steady state error. How can we do that? Well, the reason our proportional controller has stopped operating is the error has tended to zero. If you think what's happening here, we've got a very small error. The error signal here, that's tending to zero. So the control signal that we're generating as a result of that error is also tending to zero. In fact, we've reached the point where we've reached a very stable state and we are hardly applying any control output whatsoever. In fact, that control output is just about enough to balance the natural loss to energy in the system. We never quite make it. So we can't use a proportional structure because the error is tending to zero. The solution to this is to use a proportional plus integral term. And I'll write down the equation first. Control signal is proportional multiplied by error plus an integral term times the integral of the error over time. Now what will this do for us? What it means is because our error signal here is tending to zero, that term is tending to zero. So we're not going to do anything, we're going to get stuck. But this is an integrator that is summing the error. So as long as there is any error, that term is tending to grow. So what happens is that as the error tends to zero, the integrator term starts dominating the control strategy. And now, because we're integrating this area of the steady state error, this term is tending to grow. That starts to take over the control signal and it pulls us up through the steady state error. That's the role of the integral term. So let's run through that again. Our control signal is based up of two terms. The proportional term, that's going to dominate when the error is large. So it's going to dominate there and there when the error is tending to be, much larger. So that's going to pull us up or drop us down, and we'd end up in the steady state error condition. When the error starts tending to zero in this region, this term also tends to zero, but the integrator, which has been actually summing these errors, that will start growing and that will take over control and it will push us through the set point. Now what's happened here is that the error has gone from positive to negative. So now, because we've gone through the set point, the integrator term, which is integrating, starts declining, so it starts dropping off and it drops below. And we get a response characteristic that tends to oscillate nicely around the set point. So if we look at what happens in real time, a perfectly tuned PI or two-term controller will have a response characteristic such as this, where in fact that is an exponential decay and eventually you do reach steady state conditions. If you've tuned it correctly, then you will actually end up to the point where you're spot on the set point. So let's write that out again. Control signal proportional times the error plus the integral of the error over time. So you integrate the error over a long period of time. And what that does is it pulls us out of the steady state error through the set point, and the I term will start dominating when the error tends to 0, and we oscillate around the set point till we finally stabilize and settle out. So the two-term controller, proportional plus integral, is a technique to control our valve till it gets to the steady state error, and then the integrator will drive the steady state error out of the system. It always overshoots because the integrator has then got to decay, but it will neatly oscillate around the set point, and you will always finally hit your set point with a purely proportional and integral controller. Very, very straightforward control algorithm, very easy to implement. But of course it also has dangers, because whenever you introduce a time constant into a system, if you get the timing incorrect, things that oscillate could go out of control. And if you get your sums wrong here, instead of a nice decay, it could instead flip round and you get an exponential increase and your system goes unstable. Why should that be? Well, if you've got an I term that is too large, it can dominate the proportional term and it can drive us unstable. The other reason why there is a problem is that, bear in mind, the I term has been integrating all errors at all time. So even when we were well below the set point, the integral term was integrating all these errors as well. So when it finally does kick in, instead of operating using data from the most recent steady state error, it's also got all this information from when you started, from when the system was first switched on. So it's always going to be far too great at the outset, and that's why you get this large lump, but hopefully it dies away. The problem with an integral term, when you've got an integrator on, it integrates from the beginning all the way through up to now. So even though the proportional term was happily pulling us all the way up to the set point, the integrator at that point has got swamped by this heavy error data, and it tends to have a very large kink and then settles down. But if the I term is too large, it will take over and it can go unstable and oscillate. This is a phenomena that is called integral wind-up. Integral wind-up is the phenomena whereby the I term dominates the control system and it runs away, making it going unstable, and eventually it will destroy your system. So in general, the I term in the equation should really be no more than 10% of the P term. And that's a general rule of thumb. It does depend upon the system. But let's do our equation again. Control signal equals P times E plus I times the integral of E dt. I should be less than 1/10 of P. That's just a general rule of thumb. There's no specific rule about this, but if it's greater than that, you're going to get integral wind-up. If your response of your system is too fast as well, you're going to get integral wind-up. If an integral term can go crazy, it will. They're like that. They're not very predictable. They're very good at getting rid of steady state error, but if they're too large, they will make your system go unstable and critical. So take great care with them. How can we control the I term? Well, there are some traditional control techniques, but with the advent of modern computing, I want to show you a few computing techniques which are much, much easier for us to implement. One of them is a thing called the integral clamp. Now, the problem with it, with our system, is that we had P times E plus I times the integral of E dt. And the way it works is that we're going unstable because the I term is becoming too large. Well, we can solve that in software, can't we? We can say that if I term greater than I max, whatever that maximum value is, we can set I term to equal I max. It's a very simple software technique. The integral clamp simply puts a maximum value on the I term. Very simple, very easy. And all that happens is that if you look at the response of an integral clamp system, whereas it was running away before, the nice thing about it is that you still get the very, very high speed response, but suddenly it drops back and comes into control. It's quite sharp, but it does work. And it's a very simple software technique. So that is an integral clamp. If the I term, the whole of this term, exceeds a maximum value, you limit it to the maximum value, and that stops it running away. Now, another mechanism is to use an integral reset. This is a bit of a cruder tool, but it is based on an analysis of what we want to achieve. Now, let's overlay our problems. Here we have proportional only with steady state error. We added to this an I term in order to pull that through there, and then ideally it will do that and start oscillating. Our problem is that it went too fast and it starts going out of control. What the I reset does is it says, look, if you finally reach that point, the I term has done its job, get rid of it, set it back to 0. So what we say is that if the set point equals the measured variable, i.e. we've got to that point, we set the I term back to 0. We just get rid of it. So we've cut our steady state error, we've been pulled up to the set point by the I term. Instead of letting it pull us through, switch it off, turn it off, get rid of it, reset it back to 0. Again, a very simple software technique. And the response characteristic you'll get with that looks something a bit like this. Here you get a reasonably smooth response because that's PI at that point. Here it's a very sharp discontinuity because suddenly the control signal has been switched off and it just suddenly drops back down. Now, if your actuators can accept high-speed changes such as that, then integral reset will work for you. But there is an even neater software solution that you could use. One of the main reasons an I term will go out of control is it's integrating from forever. In a digital system we don't have a continuous signal, we take regular samples, a sample data system. We could change our algorithm to be more appropriate for a computer. And instead of using an integrator, let us think of it as a sample data system, a series of discrete samples. So now I'm going to say our control signal equals our proportional term times our sample of E at time n, plus a summation of all the samples of error from some time n minus 128 to n, say the last 128 samples. Because what we do is we've got a continuous error signal. What we have to do in our computer is take samples of it at regular intervals. And if we store these samples into an error array of, say, 128 elements, we drop in the most recent sample at en, losing our oldest sample. So we have in our array all the samples from time now to time minus 128 samples ago. If we only integrate over the most recent history, then we overcome the gravest problem of an I term. An I term went out of control because it integrated everything. If we use a sampled data system instead, so we have a moving window in time, we will only integrate our most recent samples, and doing that we can have a far more stable proportional integral controller. And in fact, PI controllers really come into their own with the advent of microcomputing, where we have these data structures and we use it. So what we tend to do is that we would have an array into which we store our errors. The most recent sample EN is used for our proportional term, and the sum of the array is used for our integral term. So we get proportional integral control, but with only the most recent data, not historic data. So there we have proportional and integral control. But there's another way we could control this that might be a little bit smoother, because all of the techniques I've given you, perhaps with the array is quite smooth, but the other ones have very harsh response characteristics. The clamp, the reset, put a sharp perturbation into our control system. Let's look at another thought, another way of analysing our problem. Here we have our set points. Let's home in on what's happening. As we approach the set point, we're going to shoot through it and then hopefully come back down. This is a classic PI problem. Now what we could say is, look, if we were to measure the rate of that slope, that would give us an indication of how bad the slippage, the overshoot will be. Well, if we had a very gradual slope, we're more likely to do that. If we had a very steep slope, we're going to get that. So there's a relationship between the rate of change as you approach the set point and how far you will overshoot before you start coming back down. And there is a measure of our error. So if we could predict we're shooting up too fast and slow us down, then we might have a way of bringing the integral term under control before it's done any damage. So what we're saying is that we're rising to the set point, and if we see we're going far too fast, we predict in advance there's going to be a problem, and rather than have to click in one of these very harsh resets or clamps, we slow it down before the damage occurs. And it's much better to predict there's going to be a problem and stop it happening than to let it happen. How can we do that? Well, all we need to do is to look at the rate of change of error. Go back to our graph. Look, if we're moving very slowly, things are all right. If we're going a bit faster, maybe we have a problem. If we're going too fast, maybe it's time to slow things down. So I'm going to give you another algorithm. I'm going to use the sample data version now. I'd say control signal equals proportional times the instantaneous error now plus sigma, the last 128 samples. So there is our I term. But the other thing I'm going to do is I'm going to calculate the rate of change. Now how do you do that? If I take En minus the previous sample, that is a measure of how fast we're changing. So we're taking two samples in time, equally spaced, and if that is too large, what we want to do is to reduce the control signal. So what we have is a proportional term, an integrator, and a derivative term. And what the derivative term is doing is saying if we're running away, if the rate of change is too great, we start slowing down the system. We put the brakes on. The derivative term, also known as the damping term. If we're going too fast, it slows us down. It says, oh, just hold on, wait, slow down. You're going too fast. You're going to cause trouble in the future. Let's stop you causing trouble in the future. We'll slow you down now. So what we have here is the full PID control algorithm. And we'll write it out again. It's called three-term control, the three-term control algorithm, PID, proportional, integral and derivative, where the control signal equals P times e to the n plus I times sigma, whatever the sample block was. I'm doing this as the way you do in the program, en, plus, I say plus here because you can always have a negative number in the constant. It's only a constant. That is how the equation is written out in full in its discrete term. And it is essential that you understand this algorithm, that you can write it, that you can explain what each of these terms do and how they operate and what their purpose is. Now, I don't mind whether you do it as the sample data version or you do it as the analog version with the integral and dE dt. It's exactly the same thing, as long as you understand how it works, what each of these terms are, what each of them will do, how they will affect the response characteristics to go from steady state error, proportional, to the integral, to the derivative, which will tend to slow down the integral term to bring it under control. That is the essential requirement. Three-term control, proportional, integral and derivative. So widely used is it that you can go out now and buy off the shelf PID control units that are already pre-programmed with it. All you have to do is to plug in your P, your I and your D constants, screw in your transducer, and it will give you a voltage output that matches that. Hello, welcome to the second part of the discussion on control systems. I'm going to try and review today the work we did on the previous lecture on control, and also I'm then going to show you how to use the demonstration program you've all been issued with, control.exe, because I want you to experiment yourself with different control parameters for a three-term control loop. But let's just run through the control strategies again. What we're trying to achieve, here we have the world from which we take our measurands into our controller. We take some decisions and using actuates we try and drive the world back to our desired position. What we were discussing last time was the contents of these control algorithms. Now, the simplest algorithm you can use is on-off control. Very crude. If you are below your set point, you switch your system full on. If you're above it, you switch it off. And the response characteristic looks something like this. If this is our set point, our measured variable will rise up till it reaches the set point, and it will always overshoot. So as long as the measured variable is less than the set point, the system is full on. There's no partial control, no gentle adjustment. It's either all on or all off. Just like air conditioning or central heating, it's just on or off. Why is there an overshoot? Because there is always a finite time taken for our system to respond to this, to take a decision, for the valves or the solenoids to operate, and finally we will go off sometime later. This is the response time of our system. Now we will start falling back. All the time we're above the set point, we will be off, and then we will fall below, and again there is a similar response time on the other side, and eventually we'll come on. So we tend to oscillate around the set point. And there is a direct relationship between the amount of oscillation and the frequency of oscillation. if you narrow down this line so you have a narrower oscillation, you will oscillate faster. So there is a clear relationship between the two. We drive up and then we turn off, and you will oscillate around the set point. This oscillation is known as hunting because you're always trying to find the set point. If the rate of oscillation is too great, you can cause severe damage to your system. Your system is going out of control, it's getting dangerous, you have to slow it down. So one of the techniques I showed you how to do that was hysteresis. With hysteresis, if here is our set point, and we widen the set point with a hysteresis band, a hysteresis positive, hysteresis negative. And what we said was that we would keep our system on, not just to the set point, but through it. We would let it overshoot. So while we're rising, we remain on until we go over the hysteresis band. Then, only then, do we switch off. And now the system will cool or drop, but we don't turn it on at the set point. We keep it off until it is below. So here we were on, below, on, till we're rising, and then we keep it off till it falls below, and only once you've detected it's fallen below, then we will switch it back on. So a decision as to where we switch is dependent upon the direction we were moving at the time. And what we do is effectively we're widening the set point, and as I showed you earlier, there is a relationship between the amplitude of oscillation and the frequency. If you want to slow down the frequency of oscillation, you need to widen the amplitude. And if the inherent response time won't do that for you, by adding a hysteresis band, you force the system to oscillate over a wider band, and that will happen at a slower frequency, and your system will survive. So that's hysteresis. But you need a slightly different approach if you have a bidirectional controller. That is, you can both drive up and drive down. The way, if you were to apply hysteresis to that, you would go out of control because you'll get to points where both directions are fighting against each other to drive into each other. Instead, what we do is we create another band in the opposite direction, which is called a dead band. A dead band. And a dead band is used only when you have a bidirectional system. That is, you have the ability to both drive up and to drive down mechanically or with some motor or heating or cooling system. And the way it works is that we drive up when we are below the dead band, but when we hit the dead band, we switch off. Now the system will still tend to overshoot, and only when it is over at the top will we drive it back down. The idea is that whenever you are within the dead band, both systems are off. And if you, as soon as you stray out of the dead band, one of the motors or one of the actuators will drive you back into it. So you tend again to trap the measured variable inside the set point. Mathematically, in fact, it is the same as a hysteresis band. It's a negative hysteresis band, but I've described them to you separately in order to give you two separate solutions for different problems. So there we have on-off control. If you're below the set point, you switch on. If you're above, you switch off. Hysteresis cures hunting. If it's a bidirectional system, so you can drive both up and down, you need to have a dead band to open up, and so that if whenever you're within the dead band, both motors stop and you don't move on. Then we moved on to a more interesting form of control. We replaced our on-off valve with a variable valve, variable control. And I introduced to you proportional control. And with proportional control, what we have said is that the control signal, the drive to our valve or actuator or motor, doesn't matter what the system is, the maths is always the same, equals some constant proportion multiplied by the instantaneous error of the system. So, the greater our error, the more we drive the system. With a very small error, we drive it a little bit. So eventually we get almost on the set point, but we never quite make it. You never quite make it because in a real system, there are always some time delays for response, and there's always some energy loss in the system. So you eventually get to a point where you get the steady state error. It's the integral of all these perturbations that you will always just miss the set point. So here is our set point. Here is our measured variable. We're full on here. We're driving up to the set point. Finally, we start closing down the valve as we approach it, but we never quite make it. And we always get what is known as the steady state error. Can't do anything about it. It's always present. But on the other hand, if our controller is good enough, if that steady state error is acceptable to us, it's within our margin of error, then proportional control will do. And proportional control is very widely used. But for a precision instrument, that's not good enough. If you need to precisely position a drill or a machine tool at a precise position, you've got to get rid of the steady state error. You've got to drive it out of the system. The proportional term won't do it for you. Why is that? Well, look at the equation. If the control signal is proportional to the error, and here the error is tending to 0 at that point, then the contribution by the whole of the proportional term also is tending to 0, and it hardly has any effect at all on the control signal. In fact, what we've done, we've reached the steady state position whereby we've got our valve a little bit open, and that is equally matching the energy loss in the system, and so we just drift along just below or just above it. What we have to do is to accumulate these errors. If these errors are here for too long a time, we need to use the power of a computer to say, "Oi, you've been wrong for far too long. Why don't you do something about it?" And we do that with the integral term by summing. I'm using 128 there because those are the figures I normally use, but it depends how much you want to, what sort of number you want to use there. What we do is if we integrate the error over history, then even though this term has tended to 0, if we remain in the steady state error position, this term is growing. So when there are very large errors, the proportional term will dominate the system. When there is a very tiny error, the proportional term is tending to 0, but the integrator will slowly integrate that error, and it will dominate the system, and it yanks us up through the set point. It pulls us through. So we end up with a characteristic typically like this. What's happened here is that the steady state error has grown, the integral term has pulled us through the set point, the error has now gone negative, so the integral starts decaying, and hopefully we oscillate neatly around the set point with a nice exponential decay. This is the proportional plus integral control, and this is its characteristic response. Proportional plus integral control. And that's usually about all you ever need for the vast majority of control systems. The problem with integral control is that if the integrator starts dominating the control system, your system will go out of control. Now, why should that be? Go back to this graph. If we were integrating the error with a pure integrator, we will be integrating all of the errors from the time 0. The proportional term was doing a damn good job here at this point, yet by the time it reaches there, the integral is taking decisions upon information it got from a long time ago. Now, one cure for that is to use this summation approach, whereby instead of integrating from 0, you only integrate over the last 128 samples. So at that point there, all we integrate is the last 128 samples, rather than everything from history. And that's a moving window moving with us. By using an array in a computer, this is a computing technique as opposed to a traditional control technique. By using an array, we have a moving window on the errors, and so we have more stability. If we're still having problems with the integrator going out of control, and the effect of that is that instead of this exponential decay, it flips sign and it goes positive. And what happens is you start getting that effect. Our whole system will fall over. There are some other computational techniques you can use. One of them is the integral clamp, and the other is the integral reset. Let's run through what both of them do. The integral clamp, very crude system. It says that if the integral term, where the I term is I multiplied by sigma e to the n, n128 to n, there's the whole of our I term. If that is greater than some maximum value that we set in our computer as a constant, then we set the I term to equal I max. And what we're literally doing is we're capping it. We're stopping it growing too much by using a computer. Very simple. It is a bit harsh. You tend to get a bit of a jerky response, but it does do the job. It stops it running away. That's one way to do it. The other method, this is a different method, is the integral reset. I reset. And what the I reset does is that it uses the concept, look, if we're trying to reach our set point and we have gone through it, the I term has done the job. We would have been doing this in our steady state error. The integrator has yanked us up and got us through. Once we've crossed the set point, it's done its job. Get rid of it. Switch it off. So we say that if the measured variable is greater than the set point, we set the whole of the I term to 0, i.e. you just clear the array. Bear in mind you've got this array that is following last 128 samples. As soon as you detect you've crossed the set point, you do a memset 0, clear the whole of the array out, and the I term disappears. And what you tend to get is an effect such as this. Nice smooth control up, PI, there's the I term, switched off, and it drops down. Very jerky response at that point, very high frequency components in these signals, but it does do the job. It stops it running away. So there we have 3 computational techniques using a running mean, the array of only the most recent data, not all the data, an integral clamp, and an integral reset. However, traditionally, there is a much smoother approach to doing this. Those 3 methods I've told you are applicable to computers and tend to be rather harsh in the way they move things about. A far more relaxed method of doing it is to look at the rate of change of the signal. Because let's think what's happening. If we're going out of control, what's actually happening? What it means is that here's our measured variable. If it is accelerating at too fast a rate through the set point, it's likely to go into this unstable position. What we want to do is that near the set point, if we detect that this rate of change, the dE dt of the error signal is too great, we want to slow things down. Because if we had a response that was doing that, a much lower rate of change, we're more likely to come under control. So if we measure the rate of change of our error signal, if it's too great, we know we should be closing our valve off because we're in danger of accelerating through the set point. And so we have what is known as the derivative term. Control signal proportional times error n plus the integral sigma n minus 128 to n, that's the sum of the last 128 samples, plus a derivative term, en minus 1. There is the difference between the last two samples from our array. And we do this all with our array. If we had a 128 element array, and we're always putting the latest reading into there and dropping the oldest one off, so it's a moving window in time. There's e to the n, there's en minus 1, so we just take the difference between the last two readings in our array gives us our derivative term. The sum of the whole of the array gives us our integrator term, and the most recent sample is our proportional term. So you can do the whole thing very easily within an array and a couple pointers running around the array. Very, very easy coding to do. And what happens with our response? Well, if we were going to be doing that, perhaps accelerating away, the derivative term again only starts dominating near with small errors. If the errors are large, the p term will always be the most dominant factor. Give you an order of magnitude. If that's got a value of about 10, that should have a value of about 1, and that should have a value of about a half. That's the sort of order of magnitude you need there. But you need to play with these variables to get them right, and that depends upon your actual system. But as you can see, the proportional term is going to dominate most of the time. It's only when you get close to the set point, as that value is tending to 0, so then these time terms start coming into play. And what will happen with the derivative? The integrator will do that. The derivative will tend to slow us down a bit and smear us out. It will slow the response down. It is a damping term, but it does stop the integral runaway. So there we have on-off control and three-term control, PID control. These are the key algorithms that you need to study, that you need to know about. What I want you to do, not now but in your own time, is to take away a copy of the test program control.exe and play with it on your own PC. It's a DOS-based program, but you can run it under a DOS window. It should run okay. It hasn't got any real-time operation in it. It simulates a three-term control algorithm. And what it does is allows you to enter different values for P, I, and D of your choice, and then it will trace the real-time response. Now I'll just briefly run through it. So if we go to the PC and we'll have a look at it. The program is called Control. There are copies of it available at in the university. If we run it, it asks us first, is the system bidirectional? This is my definition. Can we drive the system either in one direction or both directions? You can play with either setup, but you get the best pictures if you have a yes there, because then you get a much faster response and you see some more interesting response characteristics. It then asks you, is there a loss? By this, I mean, are you losing energy during the operation of the system? If you are, then that will be a real system. In real life, energy is always lost from a real system. So you really need to enter yes in there to simulate the loss of energy. If you want to see what happens if you don't have a loss of energy, just enter no there and you will get the most perfect control system every time. Your set point will always hit the measured variable immediately. But that's not real life. That's there for you to try. I want a real system, so let's say yes for a loss. And now it prompts you to enter different values for full, proportional, integral, and derivative. I'm going to put in a value of 10 for the proportional term. Ask me if that's okay. I am happy with that. I'll let it stay there. we have no integral term, no derivative term. Now finally it's asking us for the lag. By lag I mean the response time for your system. How long does it take to respond? Again, it's a matter of whether you want to look at the ideal situation or the real world. In the real world there is always a delay between measuring an error and responding to it. The units of delay that I've put in here are pixels. There's 640 pixels horizontally, so if you want to delay the response by 5 pixels, that's not very much, just enter a 5 in there. But that's usually quite good. And you can degrade your system by making longer and longer delays, and you can look at the different response characteristics that you'll get as your system gets slower and slower and slower. And that's quite a good experiment to do. But let's just enter in 5 pixel delay, and let's just let it run. It gives you the option of a dead band if you wish. I'm not going to play with that at all. It's up to you. If you want to enter a dead band, you can. It's equally applicable to PID as it is to on-off control, but that is beyond the scope of this module. For your own private study, you can play with that if you wish to. And here we have the effect of pure proportional control, whereby we have a very small delay at the beginning. You might be able to make out on the image a small flat line. That is the 5 pixel delay. And then we've risen to steady state error, and the steady state error is quite large with this system. It's quite surprising how large the steady state error can be. So there's pure proportional only control. Let's tinker around with this and see if we can improve it. So if I increase the proportional term to 50, let's leave all the other values the same, and as you can see we have a much smaller steady state error, but it's still there. Now if you want to, you can overlay graphs. If I press S, that saved that last graph. Let's go back to 10 for our proportional term, and now we should be able to overlay the previous graph, and we can compare the two to each other. Ignore the rubbish at the end on the far right of the screen. That's just mistakes in my program. I've just not finished the line correctly. So let's carry on increasing the proportional term to see what's happened. We've got 10, we've got 50, let's try 100. Well, we still have a steady state error. It doesn't matter how much you increase your proportional term, you will always get a steady state error. You can't get rid of it. Let's crank it up to something really ridiculous, and I suspect this will just go out of control. And what we have actually achieved here is hunting, very, very high oscillations, so high that the program actually crashes and can't cope with the maths. Reload that. Let's go back to 100 as our gain, no I term, no D term, 5 pixels delay, and there we have our response. Quite a high gain, 100, very high, but no matter what we do, we still have a steady state error. Can't get rid of it. That's the real world. But look how we have got this very sharp peak very early on. That's signs we could be going into hunting and instability. I'm going to save that graph. I'm going to now do it again without a delay, just to see if there's any difference between time delays. This is the sort of experiment I expect you to do, is to try different setups. And it's interesting that with no time delay, we still have a steady state error. It looks very similar to me. We've ended up with the same result, but without the kink at the beginning. Let's get back our initial response, proportional term of 10, time delay of 5, and look at the response, proportional only control. Now we're adding a integral term, small integral term, and we'll see the effect of adding an integrator to that proportional value. It's asked me if I want an integral reset. I don't want one at this stage. Now this is now proportional integral control, and as you can see by adding that I term, it's done the job. It's pulled the steady state error up through the measured variable, up through the set point, we've oscillated around, and we have finally settled down. Let's see if we can get that a little bit more exciting. Let's have a proportional term of 40, an integral term of about 5, short delay. We see more and more of the oscillations. I'm going to wind up the I term a little bit more. The larger I make the I term, the quicker we should settle down. But as you can see, even though we've settled down quicker, that first loop of the integrator is growing and growing and growing, isn't it? Let's increase the integral term. I'm obviously trying to simulate integral wind up here, and there we've got it. The I term has got so large with respect to the proportional term, the system has gone unstable, and instead of an exponential decay, we've got exponential increase. So let's go back to something that was stable. 40, 10, 5 pixel delay. There is a proportional term, proportional and integral. I'm going to save that, and I'm going to see whether if the addition of a derivative term calms it down. Now we need to overlay the two. You're looking now at proportional plus integral plus derivative. I will overlay on that now the previously saved proportional and integral. And as you can see, the initial peak of the PID is lower than the pure PI term. So what we've done is we've damped down the response, we've slowed it down, we've reduced the possibility of integral runaway. I'll repeat that for you. First of all, we will do it with a no derivative term. So there is our response characteristic with proportional and integral only. I'm going to save that. Now we will add the small derivative term. There it is. I think you should be able to see the first loop is already lower, but there is a time delay, isn't there? The whole thing is just like it's been sat on. So the humps are lower, but it's squished out. And now I will overlay the previous graph, and you will see that what we have done is we've damped it down. Now I'm wondering whether we can go out of control with this, remove the D term. This is proportional and integral only. This is going out of control. I wonder if we can bring it back into control with a hefty derivative. I don't know. I'm just experimenting to see what will happen. And it's done it. Well, that was a surprise. I didn't think it would with those values. So let's run through that again. That was a nice one. Proportional term of 40, integral term of 20. So that's going to get us up to that set point very quickly, but it's going out of control. No derivative term. There it is. That is clearly growing and going out of control. But if we add in a derivative term, it's damped it down enough to get it back under control, and eventually we will reach our set point. So this program, Control.exe, it's been issued to you. I expect you to use it in order to understand in better detail how proportional, integral and derivative control operate. I want you to get familiar with the waveforms. They're printed in the book. And also you should be able to derive them graphically by using this program, and with that you should get a full understanding of the three-term control algorithm. Hello, welcome back. So we've now finished three-term control. There are, however, some other terms that you need to understand, just the names without any detailed mathematics. I promise you, no more differential calculus. That's it. You've done it all. No more nasty maths. There's a little bit more to come in signal processing, but that's just adding and subtracting. But that is the end of the calculus, honest. Now, all the systems I've referred to are known as feedback systems. Why feedback? Because we're measuring what's happening in our system, our measured variable, and feeding it back to our controller. So what we're actually doing is we are responding to history, to the past. It's always a feedback system. And we look at that, what happens in our system. That means we have a set point goes into our, I'm going to combine the whole thing together. Here is our system. This is our controller plus the valves, actuators, everything. And then out of that we extract a measured variable and we feed it back. So we have here our measured variable comes out of the whole of our system. So it's history. It's too late. It's already happened. And then we respond to it. So what we're doing is we're always reacting to what's happened in the past. That is a closed loop feedback system. There's nothing wrong with that. As long as you can respond quickly enough to these deviations in real time and pull yourself back onto the set point, it doesn't matter. But let me give you an example where this might be a problem. Do you remember earlier on I showed you a shower, a domestic shower? How can we do that? How can we manage a shower system? Well, let's think about what we've got. We have a pipe in which water is flowing. That has to go through a valve. So there's a variable valve. Water then flows out of that through an electric heating element. This is how a shower works. So we feed energy into it. So cool water comes in, hot water comes out, and eventually it comes to a little shower attachment. And there we start. Well, you probably aren't allowed to do this, but never mind, it could be entertaining. There you are, having your shower, getting nice and warm and hot. Now, if that was a feedback system, how would we implement that? Bear in mind, the way showers work is you don't have a variable heater. You always have a fixed heating element. It's like an electric fire. 3 kilowatts, 2 kilowatts, or 1 kilowatt. The way you vary the temperature of the water is by the amount of water you flow through it. If you want very hot water, you just trickle a little bit of water through the heating element, and then it gets very hot. If you want a much cooler shower, you pour more water through it. So the way we control the temperature here, and let's call this temperature out, the way you would vary that is by measuring the temperature out and controlling the water valve. So if this was too cold, you would close the valve off, less water flows through because it's a fixed amount of energy going in. The temperature lift is greater, and so you get hotter water. Now you could develop very easily a feedback control system based on measuring the output temperature. Somewhere or other there'd be a little dial. I think we saw the dial where you choose the temperature you want. That's your set point. And so we have a very simple control strategy that we have an error based on the output temperature minus the set point, and that tells us the position of the valve. The greater the error, then the more we would close the valve off to make the water hotter. It would work. There's nothing wrong with feedback control for a shower, apart from one thing. It's working on history. So what happens if we've set our system up to give us a nice medium temperature shower, 30, 35 degrees C, nice and warm, invigorating, nice warm shower, and suddenly there's a perturbation. the water suddenly stops flowing. Now the main cause of that, and this is absolutely true, it's because somebody has flushed the toilet in the next room. Because as soon as that amount of water is pulled out of the system, remember I deal in the real world with real problems. We have a shower in the shower room, taking water from a water pipe, which is also feeding the flush toilet, and that is a lot of water. If that pressure of water is suddenly removed from the system, the amount of water that flows through this pipe suddenly drops off rapidly because the water is being diverted elsewhere. So that small trickle suddenly shoots up in temperature rapidly. And so momentarily, if we looked at the temperature profile, if there was our temperature, suddenly there's a vast increase in temperature due to the sudden drop in water pressure into the shower. Now our feedback system would detect that, and it would open up the valve, let more water flow, and eventually we would come back under control. So a feedback system is capable of handling these perturbations. But there's a great problem with it. It's too late. Because when you hit these high temperatures, that landed on the heads of these poor people, and they got burnt heads. That's the problem with a feedback system. It's history. It happened too late. Now, in most applications, it doesn't matter. As long as you pull yourself back, you get there. If you were just driving along on a lane and you wobbled in, that's fine. But if it's a person underneath a hot shower, that perturbation is going to burn their head. Not only will it make them extremely upset, it's going to hurt, and it will damage the sales of your shower. Because everybody will know so-and-so showers burns your head because it uses feedback control. We need to have a different mechanism in some circumstances. What we have to do is, instead of relying on fixing the mistakes after they've happened, we have to predict they're going to happen and prevent them happening before they occur. How do we do that? Well, we're moving into the realms of, instead of feedback, we're talking about feed-forward systems. Let's draw our system again. Here we have our water. We have our valve system. That goes into, here's our fixed heating element. Out comes the water, goes to the shower. Happy people having showers. If we monitor here the output temperature, and we have here a set point, we know that taking the error signal with the output and the set point will bring us under control, but it will be too late. So what we have to do is, instead of measuring the output temperature, we measure the input temperature. And we compare that to our set point. And so what we do is we measure the difference in temperature between the water flowing in before it's reached the heater, and we compare that to our set point, and we get an error. Based on that error, we then adjust the valve to give us the correct flow rate for this heating element to give us the correct output temperature. What we are actually doing is, instead of responding to problems, is we create in our computer a model of our control system, a mathematical model of how it operates. We know how efficient the heater is. We know that this is a fixed heating element. Typically it's a 3 kilowatt heating element. So we know, because we know the specific heat of water, we know how much the temperature will be lifted based upon a particular flow rate. We can calculate the desired flow rate to raise the input temperature to the desired set point and adjust the valve. What we're trying to do is to predict what happens. We know mathematically everything about our control system. We know
the heating element, how efficient it is. We know the volume of the pipes. We know the specific heat of water. Given these pure physical constants, we know precisely how many degrees C the water will rise from the input temperature to achieve the set point dependent upon a certain flow rate. So what we can do with this operation here, this predictive control, is that we can calculate a new set point for the flow. So we have a set point here for the temperature. That's what we want. We compare it to the input temperature, and using a mathematical model based on our knowledge of this structure, we calculate the desired flow rate that will give us this particular temperature, and then we open the valve to the correct amount. We're trying to predict what happens, and this is called feed-forward control because it's predictive. It's in advance of the system. The feedback system, feedback looked at the output and fed that back. Feed forward looks at the inputs. It feeds into this algorithm everything we know about the system now, and we use that to predict how it will respond, and then we take decisions on the valve as to what position it should be in before this water has hit it, and then we get a much smoother control. So now let's have our problem again. Somebody flushes the toilet next door. So we've got a nice flow rate. It suddenly drops off. We know what the flow rate is. We know it's dropped off. So we predict in advance we need to open up the valve to let more water through because the pressure head has dropped. And so we maintain the temperature in advance of the perturbation hitting our system. What else could affect you? Well, let's assume this was wired up not to the cold water source, but to the hot water source. So you already have water at a particular temperature from a hot water tank. If that temperature varies, either because somebody has put an immersion heater on, or somebody's drained all the hot water away and it's now gone cold, you can adapt your system by varying that valve, and so you're capable of drawing off your source water from any temperature source. And we throw all that information into a recipe. We have a recipe, a model of how our system works. We know the pressure, the temperature, the input flow rate, all the input ingredients are thrown in, and we stir up the cake, and that tells us exactly how long to bake it for, or in our case, how much to open the valve. And so we're predicting the future. We have feed-forward predictive control. I'm not going to go into the maths of it because, of course, the mathematical model is different for every system. Your job as the programmer is to develop the mathematical algorithm that represents the whole of this control system, and then implement that in code, feed in the inputs from which you derive the output flow rate. So there we have feed-forward predictive control. Now let's wrap this all up and look at what our whole system actually looks like. Because I did tell you the shower is the most complex control problem I have ever had in my career. And I'm serious. And I'll show you what the whole system finally ended up as. We had a set point from a dial. We have a temperature sensor that measures the input temperature. From that, with knowledge of the actual heating element, its power, the geometry of the pipe, we were able to calculate a new set point for the desired flow rate. Now, if you remember, I showed you, when I opened the shower system up, I showed you that valve, because that valve was the simple solenoid that moved backwards and forwards and let water flow in the pipe. But we need to measure how much water is flowing as well. So hopefully you might remember that also fitted to this system was a very simple turbine meter. So what this gave us was a measure of the flow rate. And what we did is we actually used that in a feedback control system we fed back the flow rate that we measured into a feedback controller, and that is what we used to control the valve. So we had feed forward control based on measuring the input temperature and the set point to give us a prediction of the flow rate we required, and we used feedback control to control the position of the valve based on the actual reading we had from the turbine meter. Then it went through the heating element, and finally the water came out of the shower to our happy people, who hopefully are not going to get burnt heads. Quite important, and so we can sell lots and lots of showers. So it was quite a complex control system. It was combined feed-forward control to predict the flow rate we needed to get the correct set point based on the current temperature of the water. Then we used a turbine meter to measure the true flow rate, and we had feedback control based on the calculated set point and the actual measured flow rate that controlled the valve, and so we controlled the amount of water that flowed in the system. But even that isn't the whole story, because there is another phenomena you have to take account of. No matter how precise your model is, things change. Nothing you can do about it. Pipes distort. Heating elements become less efficient. Heating elements burn out. In fact, as heating elements burn out, they give out more heat rather than less, till eventually they burn themselves out and they break. Nothing ever remains stable. So we always have the problem of what's known as long-term drift. That is, things change with time. It's common sense. You can draw up a model now, but they change. As time moves on, things work in a different way due to mechanical wear or changes in the electrical characteristics. What are we going to do about it? If you had a feedback system, it wouldn't matter. Feedback controllers inherently cope with all changes because they're always monitoring the actual true outcome, the error. It always measures the output. So if we find that a particular valve isn't operating as it used to be, the control signal will adapt for that. It will adapt to changes. And so a feedback system inherently overcomes long-term drift because it's always monitoring the truth, the output. Feed-forward control systems can't do that. You've written a model, a mathematical model, an algorithm. If the model changes, your program won't change. It's got to adapt to the new situation. You have to change your model to take account of changes in the system. How can we do that? If you have a system here, this is a fixed model. We have here a program that represents this shower system at the time we manufactured it. But long-term drift will change it. So what we have to do is we have to have another feedback loop. And what we do is we do measure the output temperature as well. And over a very long period of time, we compare that with the set point and we look at the trends. So we let this operate in a feed-forward control manner in the normal way, but over a long period of time, and in fact it's done over an 8-hour period, we monitor how effective this control algorithm was. And if we monitor a trend to be too hot or too cold, we change the model. We actually adapt the model. It's a self-tuning algorithm. It's a very complex problem. So we have feed-forward control that is predicting what will happen with a model, but that model is fixed. We have a long-term feedback system monitoring the output temperature of the shower, and it's looking for trends. And if consistently we're finding we're too hot or consistently we're too cold, it goes back and it changes the model itself in the computer. The computer actually retunes its own model, its own algorithm, to adapt its own feed-forward algorithm to the true picture over long periods of time. So we actually have an extremely complex controller. And bear in mind, this is a domestic shower. You can buy it now. And in England, it sells for about £180, so it's a top-of-the-range model. And it is one of the most complex control systems you will ever have in your house if you go and get one of these showers. It's quite incredible. But let's draw out our whole system again. We have an inlet pipe. We have a valve. We have a flow meter that measures the flow rate. Finally, it goes into our heating element, and then it goes to the shower. What are we measuring? We measure the input temperature. We measure the output temperature. We measure the flow rate. Now let's see what we also have. We have here a set point. Set point is compared to our input temperature, and it goes into a feed forward algorithm from which we derive a new set point for the flow. This is the set point for the temperature. This gives us a set point for the flow rate. We have a measure of the flow rate that we feed back. And that controls the valve. So we have a feed-forward control algorithm generating a set point for a feedback control algorithm. And we have a long-term drift monitor, an outer loop that feeds back the true outcome to give us a trend information that dynamically adjusts the algorithm in the feed-forward model. So it has, in effect, 3 control loops. A feed-forward loop for the input temperature that is predictive, that generates a flow rate. That flow rate is used for a feedback, PID, loop that controls the valve. And we monitor the long-term drift in a feedback manner over a long 8-hour period. This goes on throughout the day, and that dynamically adjusts the algorithm inside the feed-forward model, so that if the heating element deteriorates or a pipe distorts or furs up, we will notice that trend over the day, and we'll feed that back in to our microcomputer, and we will adjust our algorithm to take account of the changing long-term drift. So what have we learned? Feed-forward systems predict what's going to happen. You have a mathematical model of your control system, you feed in all the ingredients, and you take a decision on how to control the valve. However, if the system changes, our model is wrong, so it is susceptible to long-term drift. We must therefore continuously monitor the effectiveness of our predictive control, our feed-forward control, by monitoring the outputs. Over long periods of time, we can detect trends, and we can use those trends to adapt our model, so we have a feed-forward predictive controller that is being updated by a feedback adaptive approach that dynamically adapts our system. These are sometimes called self-tuning algorithms because they monitor their own performance and they adjust their own parameters. Feedback systems, on the other hand, monitor the output, what is really happening, and so they inherently will adapt themselves to long-term drift. If in general they're finding that the error signal keeps on sticking because the valve doesn't move as far, the integrator term will just drive out that steady state error. So feedback systems do not need to worry about long-term drift, but the problem is that they always correct things after the fault has happened. So what you need to know and understand is the difference between feed forward and feedback, and how each copes with long-term drift, and what the role is of the adaptive feedback system in getting over the problems of long-term drift with a feed-forward controller. Right, I'm now going to finish off totally on control systems. We've finished all the maths. We've talked about on-off, PID, feed-forward, feedback, adaptive, self-tuning, and all the clever things. You will, however, come across some other controllers which have the name control and are used in process plant, but are not really true control systems. But just so you're familiar with the terminology, I'm going to introduce them to you. There's only three. We don't need to understand how they work in great detail. One of them are devices known as PLCs, Programmable Logic Controllers. I want you to understand what is meant by SPC, Statistical Process Control. And finally, we must mention expert systems, or artificial intelligence, because those are also now quite important concepts in programmable control. Let's first of all deal with programmable logic controllers. What are they? Well, let's go back to the day before we had computers, before we had electronics. We still had controllers because we still had process plants, we still had factories, and they ran quite happily without using computers, and they could implement very complex control systems. I'm only going back 30-40 years. I mean, if you go into, even now, if you were to go into an old factory, you may still find controllers using pre-computer technology that are managing to achieve some very complex functionality. How do they do it? Well, believe it or not, it is all done with electromechanical components. It's all done with relays and electromechanical timing devices, because most processes really consist of move the belt so far, switch it off, turn on a motor for so long, switch it off, turn a heater on. The vast majority of factory processes don't require very complex three-term control. They require a series of sequences. Move this from here to here. Put the paint spray on for 5 minutes. Move it to there, turn the oven on. Turn the oven off, move it to there. And so there's a whole technology based around sequence control in factories. And this is achieved by using relays. Now, how can we do that? Well, let's assume we want to switch something on. So if we have a simple switch, and we say when we close that switch, that will be a relay that will close here's the relay circuit here. So this is a manual switch. When that goes on, that activates that relay, that closes that, and that goes to some, let's say, big hefty motor. Very, very simple mechanism. A switch closes a relay, turns on a motor, the motor turns. What if we also, when that switch closes, start a mechanical timer? And literally, these are mechanical timers. You'll find them in lampposts. They turn lamps on and off at the right time of day or night. It's not done by detecting the lack of sun. There are inside ordinary lampposts things called solar dials, which are just 24-hour mechanical timers. And as they rotate around, as in, you can see these sometimes in the home, in some very low-cost, cheap mechanical day clock timers. They're just mechanical, and as they move around, eventually a brush hits a contact, and it switches on a relay. So why don't we start a timer off as well? And let's have here another switch. So what's going to happen is that this switch turned on the motor, so now something's happening, but the timer's timing. When that timer finally times out, that switch will close. We could have made that be a relay that when that closed, opened. So that closure makes that open. Now if that was put into this circuit here, hopefully you'll see we have this switch will turn on that relay, will turn on that power, turns on that motor, and eventually the timer times out and that switch is open and turns the motor off. So what we have by using a motor, a timer and two relays, it's not a perfect circuit, I'm trying to give you the idea, we have the ability to time how long a motor comes on. Now, the next thing we could do is that we could then have this close another relay and start off some other process further down. So what you will find in these very old factories, literally somewhere in the corner of the factory will be an enormous cabinet, and it's full of relays and timers, millions of them, well not millions, tens and tens of timers and relays, all wired together in clever manners such as this drawing, such that when a relay is closed it will turn on the motor and start a timer. When the timer is turned off it will switch off that motor but then start that sequence, and so on. These things were known as sequence controllers, and there was a whole art based on designing these things. And what you actually get, I haven't shown you the power supplies, but what you actually get here on this side of here, you would get an enormous big 24-volt power supply. On that side you had, and these are enormous big brass rods, you could actually grip them in your fist. Go to an old factory, you'll still see these. You had Norfolks there. And what would happen is you'd have your cabinet, you'd start with your cabinet be empty. You drop down one side a live 24-volt supply that carried tens of amps of power. So these things were dangerous. And the other side was the 0 volts. And you literally strapped across these, and I'm talking about relays in these days that were this big. They weren't tiny little things like the ones I've shown you on PCBs. They were big. And these would be welded, not soldered, welded onto these buzz bars, as they were called. Relays, solenoids, timers would all be interlinked using these simple links such as these with just very thick wires, and you would end up eventually with something that vaguely looked like a ladder, because you would have these two big power supplies and you would have strapped across them these series of rungs, and all along these rungs would be the relays, the timers, the motors would be here, and occasionally you would get a wire, would strap one down to another, so that when that closes you get a signal there which would go on to here, and so on. So what you ended up with was what was known as the ladder. Literally the ladder. And that's what they do. They used, when they wanted to change the system, they would get out a ladder, prop it against the side of the cabinet, climb up it and start welding different relays and motors onto the system. They were horrendous. Very dangerous, very skilled job. And the people who maintained these things developed what we would call a programming language. It wasn't programming in this terminology we know. They weren't programs in computers. But they developed a program language that represented these ladder structures. And this was called ladder logic. And it was in fact drawings such as this. They were literally, you drew a ladder, you drew the lines which they called the rungs, rung 1, rung 2, rung 3, rung 4, and along the rungs they drew, in fact it was a graphics language, they literally drew in symbols that represented valves, solenoids, relays, and how they were interconnected. Now I think you might be able to appreciate that all the functions I referred to are very primitive computing functions. Very primitive logic functions. If something is on, turn something else on. If something is off, turn something else off. If relay 1 is on and relay 2 is off and switch 3 is on and switch 4 is off, turn on motor 5. Turn it on for 5 minutes. These are trivial computing tasks. So what was born out of a mixture of this strange ladder logic concept and the birth of modern computing was the Programmable Logic Controller, the PLC. And what a PLC is, Programmable Logic Controller, is a computer that is full of logical switches, relays, solenoids, motors, whatever. And you program it using ladder logic. And instead of having lots of wires from your cabinet in and out, all the inputs and outputs are taken to nice clean little edge connectors, and then you can actually wire in the real connections to your factory. So what a programmable logic controller is a modern computer that is designed to implement an ancient control strategy. That is ladder logic. And in fact, they are programmed using a graphics user interface where you draw the ladder logic diagram that they used to use in factories decades ago as a graphics user interface with lots of pictures of the two buzz bars. You actually do it. You actually get a graphics user interface and you draw using the mouse the two bars, the ladders, the rungs, and then you pick up icons which are relays and motors, and then the whole thing is compiled. It's like a 4GL language, a fourth generation language. The whole thing is compiled into a machine code that mimics the operation of the old-fashioned factory controller, and that is a PLC. So there's a very wide market for them because there is years and years of investment and knowledge in this ancient ladder logic technology. And a PLC, a programmable logic controller, is a unit that actually compiles programs that literally look like that. You draw pictures like this with relays. I haven't got all the symbols in the top of my head because I don't like this sort of programming, but you actually draw all these symbols with the motors, the switches, the motors, the relays. These are limit switches. You can have AND gates with them. I didn't mention all this, and you take them into little boxes. There's only about 30 or 40 primitive symbols that have been invented in ladder logic, and a PLC compiles that into a digital code and implements the whole thing in a computer. So our enormous rack that you used to have to climb up with a ladder now comes down to a box about that size, usually running a reasonably powerful 16 or 32-bit processor. Programmable logic controllers, then, the modern equivalent of the old ladder. Now, another term you might come across is Statistical Process Control, SPC. This, in fact, has got nothing to do with control at all. It's merely here to confuse you, but you do need to know about it in general, not in specific. It doesn't. The argument behind SPC is they say, why should we bother to spend all this money on very complex equipment controlling our process when it's not really that important? If we're making a precision product, it has to be finely milled down to the last micron, yes, you'll need a controller. But if all we're doing is filling a bag of sugar or stamping out a plastic toy, who cares if it's a little bit smaller or a little bit bigger? That's not the issue. The problem would arise as if we started to make things that were far too big or far too small. So what we do, rather than have a very, very tight set point, we still have a set point, our desired perfect child's toy or bag of sugar or whatever it is, but we apply to it a tolerance band, a very wide tolerance band, and we say as long as we're anywhere within that band, who cares? We just don't care. Why don't we just, instead of having very expensive equipment, just make the things? And we'll make thousands and thousands of them. And then we'll look at a few of them, we'll sample the batch every now and again, say 1 in every 1,000 or 1 every 2,000, and we'll measure it. And we will put our expertise and our money into the measurement of the product rather than the control. And rather than controlling every single product, we'll just measure 1 in 1,000. It's much cheaper. And you only need to do this if it's a product that's not that critical. So we measure it, and we measure the tolerance. So what we will tend to do is, you can go into factories and see these things, is we build up graphs. We say, over time, they were all generally around about here or here, and you tend to get these trend graphs. And you actually see them in factories where they average out the readings. They say, as long as the product is within the tolerance band, that's fine. The whole idea of SPC is that if you do this, you should be able to predict trends such that you can predict sometime in the future you're going to go out of tolerance. So rather than trying to control every single product, we simply examine 1 in 1,000, 1 in 2,000, and we draw these graphs, and we try and predict that sometime in the future things are going to go wrong, and before they go wrong, then we go back to our process and adjust it to get everything back down to the middle tolerance band. Then don't bother with controls again. Start manufacturing thousands of thousands of thousands of, as long as the outputs that you're sampling are generally okay, that's fine. So that is statistical process control. It's a statistical concept. Rather than controlling every single minute part of the process, we just let it run. But we sample the product on the output. We don't sample every one. We measure 1 in every few thousand. We draw these trend graphs, and we try and predict something's going to go wrong. And then, well before it goes wrong, we go and correct the process. Now, these are very long timescales. These are months. If you go into factories using SPC, you will see charts on the wall that have these trend graphs fitted, and that's exactly all they're doing. They're looking at the quality of the output of the product. So they're trying to predict when things will go wrong, but they do it at a very, very low cost. It's very efficient for mass-produced, non-critical products. Now, the last term I want you to come to grips with is artificial intelligence or expert systems. What are they for? What are they all about? You've heard, or might have heard the term. Let's go back into history. All of the systems I've told you about up to now rely on a mathematical model. Whether it was feed-forward, feedback, predictive, adaptive, whatever it was always based on maths. So we could draw a general concept where we have a process, and we can represent our process by some unknown function of time and space. We don't know what it is. We put some inputs into it. Here's our controller, our factory and everything. We measure some outputs. We feed back into us. So here's our factory. This is our controller. And what we're trying to achieve is the inverse of that unknown mathematical function, and thereby perturbing on it to try and cancel it out and get everything on. Now all that is based on horrible mathematics. Even the 3-term control algorithm, it's only itself a simplification of these mathematical functions, but they're usually good enough. Now what happens if we don't know anything about the process? If we can't write either a mathematical model or an algorithm or nothing, we just don't know because we're stupid, we do not know how it works. We can't use traditional mathematically based controllers. And there are many processes out there that we just simply don't know how they work. One of the best examples is cement kilning. The reason I'm choosing cement kilning is that it is the very first process that artificial intelligence was applied to about 10-12 years ago. It was the first time the technology was used to control a cement kiln. Cement kilning, up until then, was simply handled magically by the operators. There's no way it was ever modelable in any way. No traditional control system would cope with cement kilning. How is cement made? Just a quick resume of that. Cement is made by having an extremely long pipe, a furnace, that's about 1/4 of a kilometre long. It's about 3 meters diameter. and it's on a very slow camber. And we throw into it at one end limestone and coal, and it slowly turns around. There's a furnace in the middle that burns it, and what drops out the other end is free lime. So we drive the carbonate out of the limestone and we get out calcium oxide. That comes out in little lumps, and that's ground up into powder, put into bags, and that's what we buy as cement. So we take calcium carbonate from either chalk or limestone, mix it with coal, burn it in these furnaces, and out comes lime. Now we know the maths, we know the physics of it, we know the chemistry of it, but nobody knows what really happens inside. There's so many parameters. I mean, you just never know at any time what is the actual mixture of lime and coal. It's always getting mixed up all the time because it's slowly turning. Big layers of rubbish build up on the side of the kiln. They can be actually tens of centimeters thick, as this lime coal sludge builds up a crust inside the kiln, and then when it gets heavy enough it breaks off and puts out clouds of lime and free lime and carbonate and coal everywhere. It's a horrible process. They're filthy plants. Nobody knows how they work. There's never been any successful attempt to control them with a real controller until Expert Systems. What did they do before then? Well, what they used to do is the operators used to know how they work. So they go to old Joe, who sits in the corner, who's been working in this cement kiln for years and years and years, all his life. He knows how to make cement. I mean, everybody knows how to make cement. We made cement for millennia. You just take a big fire, you throw in lime, you throw in coal, you have a lime kiln, you burn it, and the dust at the bottom is cement. There's nothing new about it, but how do you precisely control it? Well, look at the parameters. What Joe would say, he'd say things like, well, if the lumps coming out the end were too thick, that means you've not driven off enough lime. You've not driven off enough carbonate, so it's too chunky. What do you do about that? Well, you could do one of two things. You could either put in less limestone, or you could put in more coal, because you've got the wrong mix of coal and lime. But Harry, who's in the other corner, says, you can't do that. Look, if the temperature is too hot, you've got to reduce the amount of coal in there to cool it down. So what you actually ended up with, and then if you go to one of these factories, one, wear a hard hat, two, wear some very old clothes, because there's a cement film everywhere. And three, in the operators panel, you'll see there's 4 or 5 old boys who've been there all their lives, and they're arguing all the time about what to do, because they have a set of rules. Let's write down what some of these rules are. They say, if it's too lumpy, then less lime. That's one rule. Another rule is, if too powdery, then less coal. But then there's some other rules. If too hot, then less coal. Or if too hot, then more. Don't try and write these down. I mean, I'm just writing down the rule. And then you can build up a whole set of just general concepts based on some basic measurements. But they conflict with each other. What happens if it's too powdery, which means you've got to put more coal in, and it's too hot, so you've got to put less coal in? Well, if you were trying to do a mathematical model, you couldn't do that. You couldn't have the concept of saying more coal and less coal, because you're always trying to get a perfect answer. Never mind about that. Expert Systems solves that problem, because what Expert Systems say is there isn't always an answer. What you have instead is a thing called an inference engine. And in this are all these rules that conflict. and we feed in our measurands. What are our measurands? Measures of lumpiness, this is crude as that, and measures of heat. And the output is how much coal and how much lime. And these rules they fight with each other. Because given different circumstances, one rule saying, give me more coal, and another rule saying, but I want less coal. Never mind. Let them fight it out. Because what will happen is if you've got all the rules in the inference engine, eventually one of those rules will win out. And it works. It really works by using very crude terms rather than saying precisely if it's too cold, raise the temperature to 79 degrees C. What the rule says, if it's too cold, turn the heat up. Turn the heat up. That's not a mathematical concept. It's just a general thing, a general number, vague concepts. But if you have enough vague concepts in an inference engine, eventually they reach an equilibrium and the system comes under control. And now you will find the Blue Circle expert system is in use all over the world in cement kilns everywhere now because it actually works. It was the first real application of artificial intelligence in the world, the first one in process control, and it is now widely adopted as the technique for controlling unknown processes that you cannot mathematically model. So we've reviewed three different things now. Programmable logic controllers. These are modern equivalents of the old-fashioned ladder logic, where you had a big cabinet in the factory where you literally climbed up the ladder and you welded on relays and solenoids and motors and timers. All that's been converted into a graphics user interface that is compiled into a language that is run in a small little computer about that big. That is the modern equivalent. Statistical process control isn't really an online control system. It looks at the quality of the product as it's produced and tries to predict based on trends when things are going to go out of tolerance, and so it gives you advance warning when you should go back to your process and tweak it and do some maintenance. Finally, we've talked about expert systems or artificial intelligence. These use inference engines with sets of rules that conflict with each other. They're applied to the processes that cannot be mathematically modeled, and they bring these processes back into and under control.